So we saw in detail how you can do the modeling, how you can check the results, what are various kind of loadings, what you can apply on your member. And we also validated the results with the manual calculations. I have also uploaded the Excel for Beams yesterday. So you can also download it and understand how we will be doing the manual calculation, and you can validate the results in STAAD.PRO. So we did that for a simply supported UDL, for point load, uniformly varying load, fixed load, fixed supports, fixed support at both ends, cantilever member, overhang member, continuous member. Okay, so today we are going to start with static analysis using STAAD.PRO for frames. Okay, so what is a frame? Frame is a this is a first example is our 3 point member, 3 member frame. So column, beam, column. So this is the thing what we want to analyze today. This is also called as portal frame. Okay, so let me open OneNote. Okay, so yesterday we discussed all these things. We discussed in detail regarding global axis, local axis. I hope everyone of you remember. We understood all these 6 parameters: the shear force in major minor direction, the axial force, the moment in major minor direction, and the torsional moment. So all these 6 parameters we understood in detail. How are the axis, local axis of the member? Then we understood how you can see the shear force diagram, the bending moment diagram in STAAD.PRO. We understood for a pin connection. Now this is conceptual topic. For a pin connection, you know that at the support, your bending moment will always be 0. But at the fixed support, because it is fixed and the rotation of the member is not allowed, you will have certain moment over here. The red color you can see, this is the straight line. The at the support there is certain moment. Shear force you can see for UDL along the length of the member, the line of the shear force diagram is inclined straight line with a certain slope, and bending moment is curve. But for point load, you have straight line for shear force, and for bending moment you have a slope line. So I hope you all know these theory. We also understood as the span increases between the overhang, the bending moment increases, and when the span is more, you can see this kind of bending moment when certain part is hogging, certain part is sagging and hogging. I hope you understand. So today we will be continuing with frame. So session 3. So today we will be discussing regarding frames. Okay, so this is my first frame. Where my both these supports are pin supports, and I have some point load at the top. Okay, so this is my example. Now let me also open the I have similar Excel like yesterday for frames. So let me open that Excel. Yes. So this is my frame. Let me model it. What is my length of the member? 1.5 meter. Height is 1.2 meter, and point load is 10 kilonewton. Okay, so let's open STAAD.PRO. New file. Now I'll write this as frames. Choose the folder. Let me make a new folder for session number 3. As per my plan, I wanted to finish this yesterday, but we went in much detail, and so today we will continue it. So my first point, point number 0, my next point is at a height of 1.2 meter. So in y direction, I will write 1.2. Okay. And again, at 1.5 meter, and this will be 1.2. My third point and my bottom point, 1.5 meter. This. So these are my 4 points of my portal frame. So just connect them. Add beam 1, 2, 3, and 4. So I have a general rule. Whenever I am modeling, whenever I am drawing any columns, I always start from bottom to top. So whenever I see, if I click any of my column, you can see over here, the green part is at the bottom and the blue part is at the top. So starting point is at bottom, ending point is at top for both the columns. Green is at bottom, blue is at top. And whenever I am drawing beams, beams should be from left to right. So here you can see it is green at left and blue at right. So left to right. And whenever I am having any beams in other direction, in Z direction, it will be from back to front. I will be explaining you that later on when we draw any 3D element. So let's see this from front view because we will always be working on 2D right now. Okay, so this is my member properties. I think I will again go in section database. Indian ISMB 100. Let me just quickly confirm. Yes, ISMB 100. Add, add, close. So this ISMB 100 I want to assign for all 3 beams. So one more method to assign is assignment method. I will directly click assign to view and assign. Yes. So all my 3 members are assigned with ISMB 100. Material is of course steel for all of them. Specification, we are not giving anything right now. In supports, go in create, pinned, add. Support 2, use cursor to assign at both the bottom parts. Escape. Go in loading, load case detail, add, load case 1, add, close, load case 1, add, member load, concentrate force, -10 in global y direction, add, close. So I'm doing this quickly because this we have already understood yesterday. Concentrated load GY, it's a question mark. Use cursor to assign, click on assign. It's now showing assigning. Go on any of your member and click where you want to assign it. It's assigned, escape. So yes, this is the thing. Go in analysis, define command, perform analysis, no print, add, close. So analysis command is also given. Now you can, okay, one more thing. This we are working in 2D. So instead of space, I will write plane in command files. So go in command files, save it. First line you can see it's written STAAD space. So delete space and write plane and save it. Now you can close it. Why we are writing plane? Because we are working in 2-dimensional, and if you don't want to get any warning, then you then need to tell STAAD.PRO that you are working in 2D and this is your plane. Okay. Now you can go in analysis and design, run analysis. So analysis is done, 0 errors, 0 warnings, 0 notes, done. Go in post processing. Okay. Now this you can see your deflected shape. Press control and scroll your mouse. So the deflected shape will be visible to you. You can see from bottom it is deflecting like this, downwards, and again like this. If you want to see your moment mz, this is your moment mz. If you want to see shear force, vy, vy is your shear force. Let's go back to the Excel. Okay. Now you can see here in the figure the bending moment diagram. Okay, one more thing I want to specify. In frames, the most important thing always what we look up for is the bending moment diagram. You should understand how this bending moment diagram is created in frames. Always, okay? And the shear force diagram also I will be showing you, but most important thing is bending moment diagram. Now you might be seeing some difference, and I want all of you to point out and tell me. This is the bending moment diagram. You can see the shape. And now when I go in my STAAD.PRO, and if I show you my bending moment diagram, it is something like this. Do you find any difference? Do you find any difference, and tell me what is the reason for this difference? Why do you see bending moment diagram for all my columns as well as my beams? So you can see columns and beams both are showing bending moment diagram in this way. But if you see in my manual calculation, the bending moment diagram is only one-sided. Tell me the reason for this. Quickly, if anyone wants to tell, I will give you 1 minute. Otherwise, I will tell you the answer. If anyone has any answer, you can share. I want every one of you to contribute, communicate, tell yes, no, whatever is the thing.
When we place the load on beam, it will drag both the columns in. So it will show like that in the StatPro.
So, which is correct? STAAD.PRO is correct or the manual calculation is correct?
As per my point of view, StatPro is also correct. When we use this manual correction, we will see only the load on the beam, not on the columns. So instead, it's showing the both loads.
Okay. Now let us see the reason. The reason is very simple. If you see at this support, it is a pin connection, but if you see at the other support, it is a roller connection. But if you go in my case, in STAAD.PRO, we have given both the supports as pin connection. Because both the supports are pin connection, that is why there is difference in the analysis. The STAAD.PRO and manual calculation should exactly match. If they are not matching, either STAAD.PRO is wrong or manual calculation is wrong. Right now, what we are doing, the support condition is different. If you want to see this thing, you will be seeing in other example where portal frame pin. This is my case right now. Portal frame, both the supports are pin connection. Because both the supports are my pin connection, there will be horizontal reaction at both the supports. Because there is horizontal reaction at both the supports, there will be certain moment developed in my column as well. So generally what happens, now if you resolve this member, how it will be? You will get upward force and you will get one horizontal force because this is pin connection. Same horizontal force you will get over here in other direction because this is pin support. Now each member is solved differently like this because of this point load, and wherever you have this junction is treated as fixed support. It is slightly treated like this, rigid connection, not completely fixed, but it is treated as rigid connection. So STAAD.PRO does this kind of calculation for your member. And now what are the forces in this member? The forces are, this is one point load, This is one axial force. This is one point load. This is another point load and axial force. Now for bending moment diagram, this is considered as cantilever beam. Because of this point load, you have this kind of bending moment diagram. Because of this point load, you have this kind of bending moment diagram. Generally, whatever bending moment diagram you have at this node, that same will be transferred over here. So it will be transferred over here. Whatever you have over here, it will be transferred over here. Because of this point load, the bending moment diagram will be like this. So this will become like this. Now what will happen? This is my case 1. Okay, I'll just copy this part. And in my second example, still do this. Now what I will be doing is this second support. Now I will make this as roller support. Because this support is now roller support, this force will not be there. No, it will just move. Because this force is not will there, this force will be there, but the value will be 0. So it is as good as not present. Because these two forces are not present, this will not be there, this will not be there, this will not be there, this will not be there. Okay, now because these moments are not there, here it will become like this. So this will also change and it will become like this. Okay, this is one of the reason. Now see, this is not exactly fixed, because for fixed support you always get a moment over here, but this is rigid. So there is also a difference between fixed and rigid. Fixed is completely infinite stiffness, right? It means it is completely fixed, it will not rotate anyhow. But rigidity is your natural stiffness, some finite stiffness. Okay, I hope you understand this, but if you don't understand, later on when we discuss, you will be able to understand. Okay, because in general, if you see this kind of fixed support, it will always have certain moment over here, but right now we are not having. Why? So I think this is also not good to show this as fixed. It is rigid. So I will not show this as fixed because this will give a wrong representation. So I will mark this as something like this, rigid. Okay, same thing above. I will just mark this as rigid. Because in general, if you are having a beam which is fixed on both the ends, and if you are having a point load, always the bending moment diagram will be like this. At the supports you will have some moment, and at the point load you will have some moment. This will be the case. But for normal beam, at ends you will have zero moment. It will be like this. This we discussed yesterday. Okay, so now let's see this in STAAD.PRO. Okay, one more thing. Values I will not be explaining you right now. Maybe we will do for one example, but later on you can check it on your own. What is more important is the figure, the way in which the bending moment diagram is created. If you want to see the values, you can go in annotate, beam results, maximum, annotate, close. So 2.537, 2.53. This is matching. MBMD 1.22, 1.213, 1.213. So this is also matching. Now let's match the reactions. Reactions reactions, we will go in reactions. Okay, and if you want to move this, you can go in select text, choose the box and move it. Choose the box and move it. So 1.011 and phi, 1.011 and phi. So these are also matching phi. So all the values are matching over here. Now same example what I want to do. If you go in analytical modeling, support, let's try with roller support. Now how will you assign roller support in STAAD.PRO? Click on create. Here you have option of fixed where all the members are restrained. Second option you have of pinned where the forces are restrained but moment is released. But now you have the third option of fixed but. Here you have to decide yourself what you want to fix and what you want to release. Because this is my roller connection, all the moment will release. First of all the moment will be released. And because it is a roller connection, movement in x direction is allowed. That is why fx will also be released. So only thing what will be there is fy and fz. This is a 2D model, so fz is not important to us. It is only fy. Add, yes. Support 3, use cursor to assign and choose over here. You will see this kind of support. Okay. Now let us run the same model and check. Okay, done. Post processing. Okay. You can see deflection because it is not supported over here. It is just moving because of the load applied. It is just moving. The green line, if you are able to see here, it is fixed, but here it is just moving because of the load applied. And mz, you can see only bending moment is there in your beam. This is 0. Okay, I hope this is clear to all of you. But now, very important thing, let me explain this in detail. Why we are doing in this way. Let me take this screenshot. Muhammad Abuzar, your question, let's answer it now. You have 6 support conditions, 6 degrees of freedom. If you have any node, any support, you have 6 degrees of freedom. What? Let's draw the axis first. This is my y-axis. Okay, these supports are always related to global axis. So y-axis, x-axis, z-axis. Okay. So if you have any support, what does this mean? Fx, Fy, Fz. If you are having a support, Fx means you will have the movement in x direction will not be allowed. This is force in x. If you are having a pin support, let's start with roller. Okay, one thing, how to explain. Okay, first example is now we are discussing regarding two-dimensional. First example is pin. Second example is roller. Third example is roller in other direction. And fourth example is rigid. Okay. Now, whenever we are dealing with 2D, whenever we are dealing with 2D, what is important for us is only force in x direction, force in y direction, z is not there, and moment in z direction. Why? Moment in z. Now assume you only have this x and y. We are not having z because you are just modeling your member like this. It is not along the space. Okay, you are only having x and y. You do not have z. Now, what will be there in this case? You will either have what kind of forces you will have over here? You will either have force in x direction, y direction, or you can have force in this direction, or you can have moment in this direction. These are the only things what we have. Generally, when we study, we represent this as Fy, Fx, and here we just represent M0. This is what we represent, if you remember. So, what this M0 means? It means moment in this direction. But in actual, if you everything in reality is only 3D, na? Nothing is 2D. In reality, this you have some dotted line over here, which along which you are having this moment. If you have your thumb, left hand thumb, or if you have your left hand thumb in the direction of black line, what I am showing, your fingers will show the moment, and that moment will be this moment. So in reality, this is equal to mz. In reality, this is equal to mz. So we write m naught when we are studying structural analysis because we are never studying 3D. We only study 2D when we study initially. So this we write as m naught because z is not there in our picture. But in reality, when you want to apply in real world example, this becomes mz. Tell me, is this concept clear to all of you? Okay, I will explain you where you practically use all these cases. These cases are all practical cases. Nothing is fictional. Okay, now what will happen in first case? In your first case, if you are having pin connection, you will have Fx, Fy. So what you will release in this case? You will only release, you have two terms now, restrained and release. For a pin connection, you will have forces in Fx, Fy, but you will not have any moment because if you have for this kind of member, if you are having uh, any member attached, this member can easily rotate anywhere, right? But this member cannot move. It cannot move in any direction. It cannot move like upward or downward because it is fixed. But rotation is always allowed. So release. What you are releasing in this case, you are only releasing mz. So mz is released in case of pin connection. So if you are having pin connection, in release you will only tick mark mz. Mz will be tick mark. Mz will be ticked, and the all other things will not be ticked. I hope this is clear to you. In second case, what we do, roller. Now in roller, Fx force will also not be there because if you are having this kind of support, of course rotation is allowed and also movement is allowed. If I pull in this direction, what will happen? This will just move like this, and maybe it will come here because it is rolling is allowed. You have wheels over here. If you apply any force in this direction, it will just rotate. But if you apply any force in upward direction, it will not move upward, right? So in this, you will only have reaction in Fy, and your Mz moment is released because you are able to rotate as well as uh, fx is release and mz is also release. Only two tick marks. In third case, similarly, only force is there in fx. If you pull upward, it will just move upward. Rolling is allowed. And here, moment is allowed, of course. Force in y is allowed, and moment in z is allowed. In final fourth case, now if you are having some element like this where you have fixed, now if you try to rotate like this, even this rotation will not be allowed because it is saying it is completely fixed. Rotation will not be allowed. So in third case, you will have like this: fy, fx, and moment mz. All are released, and then free you will have nothing. So it will just be a dash. So in release, you have to take nothing. Tell me, is all these four cases clear to all of you? Are all these four cases clear to all of you? Now let me explain you practically where you have a pin connection. Okay. All of you might have seen this kind of device. Okay. And maybe some object is pinned over here. Normal pin connection. Have you seen this kind of device? This is pin. I think pin is clear to all of you. Now roller. For the same case, if you have some wheels at the bottom, then this can become a roller support as well. Let me show you any image of roller support in reality. This is an example of roller support. It is a bridge member where this kind of rolling. If any force is coming, slightly this wheel will move. Right? This is an example of roller support. In this case, you will have only one reaction. So in this example, you only have this member. Because of something, some external force, if you apply any external force like this will slightly move, but it will not carry the force. This is one example. In bridges, you might have seen these examples. Let me show you one more. This is another example of roller support in real examples. I hope this is clear to all of you. Kindly confirm is this is clear to all of you. Now coming to 3D. This we discussed related to 2D. If same example we have for 3D, what will be the differences? First, I will explain you a fully pin support. This is a complete pin support in 3D. So in this case, now what you will do, release. I will only discuss related to release now. Or let's discuss both restrained and release. In this, now what will be restrained? Fx, Fy, Fz. All three directions are restrained and release will be Mx, My, Mz. If you are having any member over here, This member can rotate in any direction, in all the directions, 3D, but you cannot pull it outside. So rotation in all directions is allowed, but pulling outside is not allowed. Second example, now one complex example. I hope you understand this. Even if you don't understand, it is fine. Okay, this is my pin support. This is my another pin support, and I have this kind of pin between them. And on this pin, I am attaching my member. Okay, this is some kind of base plate. On this base plate, you are having this kind of pin. You are having this kind of thing, and this is your pin. Okay, directions are, this is y, this is x, this is z. Now what is fixed in this case? Of course, fx, fy, fz. These are restrained. You cannot pull this member apart, but rotation is allowed. Where is rotation allowed? Rotation is only allowed in which direction? Z, along Z line. If you place your thumb in this direction, this kind of movement is allowed. This kind of movement is allowed. So MZ will be released. But if you try to rotate in X direction, if you try to rotate in this direction, if you try to twist this member, twisting will not be allowed because this is a pin support. No, it is not a spherical support like in this case. For this object, if I try to twist this, it will easily twist. No. But in case of cylindrical support, if I try to twist in along its axis, the twisting will not be allowed. So here MZ, MX is also restrained. And also if you try to move in Y direction, if you try to move in Y direction, that is also not allowed. MY is also restrained. So only thing what is released is MZ. Tell me, is this clear to all of you? Okay, just answer and tell me, is this clear to all of you? A little complex, but if you understand, it's well and good. Now, okay, Ramarjun is asking why we use ruler support. I will explain you the advantage of ruler support. Now, when we will, okay, this is the conceptual part. I hope it's clear to all of you. So, depending on type of your support, you have to choose from these things what you want to release. And if you don't take anything, that will be considered as restrained. So for my roller support, all my moment will be released and X direction will be released. Okay. Okay. This was for 2D. Okay. Let's come back to our discussion. That is why I have chosen this change. Done. Okay. We have also seen the value. Now, for the same point load, let's check the value. Okay. How to check the value? Okay. Let's check manually. Now this is pin support. If you go in post process, okay, analysis has to be done. Analysis, run analysis, save the model. If you go in MZ, this is your bending moment. If you want to see the value, The value is 3.75. Okay, I want every one of you to remember this. Let's take a screenshot. So easier. Second example, now what I will be doing, support condition, I will change both support to pin. Use cursor to assign. Yes, now both the supports are pin support. I will run again. Run the model again. Now if you see the bending moment diagram, this is the bending moment diagram and the values. Okay. Now why we sometimes use roller and why we don't use roller some other times. Now you can see this beam is having more moment over here, but when I am having roller supports, the beam moment is reducing. What if I am having a beam, all the beams, whose capacity is 3 kilonewton meter. So amongst this, what is this red color 3? The bending moment capacity. Now what is this 3? Now tell me which one is good, the left side or right side? Which one will work, left side or right side? I am having a beams, I am having column whose capacity is 3 and I am having the forces as shown in the figure from our tab. So what should I prefer? Should I prefer the left side model or the right side? Of course, I will prefer the right side model. This is good. This will not work because here the capacity is 3 and I am having the bending moment of 3.75. So this will just bend and fail. But the right side, it is having 2.53 and I am having capacity of 3. So this will work. So just because you changed the type of support, one became good and the other became bad. Now another example. The same example. Okay, a very small means some silly example. Here the capacity is 1, and this capacity is 4. 1, 4, 1. I'm having a heavy beam, but the columns are very weak. So now tell me, left will work or right will work? Left support is, this is a pin support and this is a roller support. As I showed you in the figure, maybe some support like this kind of support. In reality, this kind of support. In bridges, you have seen these kind of members. These kind of members. So in modeling, you model it like this. So now, and the second example is both are pinned. So now what is happening? In this member, the moment is 1.21 and the capacity is 1. So this will not work. And here the moment is 0 and all the moment is only in the beams. So this will work. So if you want to have these kind of configurations, then you can use roller support. This will not work. So that is the reason where sometimes we want to use ruler support because it gives us advantage in our modeling, in our designing. And this is one of the example why rollers are used. There are many other examples. I will be explaining you as we discuss it.
Sir, I have one small question. Can I ask?
Yes, yes.
In the rolling
Your
in
name
3D,
first.
Shravan Kumar.
Shravan Kumar. Yes.
Yeah, in 3D space frame, when have a roller support in the minor direction, we should release, right?
Yes.
FZ.
Here you can see this is a roller support. So here
Yeah.
you will only release this real example. You will release your
Only
fx
vertical we have force, but
and
horizontal in both directions it is not there, right?
horizontal board. I'm telling you what you can release in this. You
Yeah.
can release fx and you can release
FZ.
mz. These two things you can release. My you cannot release because
FZ,
uh,
I'm asking FZ.
hmm, fz you cannot release
Why? Because it's a horizontal direction, right?
because this kind of
No,
roller it
FX and
cannot
FZ
move in
both
this
are.
direction, right? This
Sir,
is my fz.
no, FZ, yeah,
Can this
FZ. Okay.
connection displace in this direction? Can it come out like this?
So there is a reaction.
Yes, there is a reaction.
Okay.
Some reaction will be developed in z direction, and for that reaction you need to design your base plate, you need to design your members. So this reaction will be developed. Only reaction which will not be developed is fx. In reality also certain fx will be developed because there is frictional support between them na?
Yeah,
So
yeah,
maybe if you just apply
yeah.
100 kg of force, this object will not move.
There is
It
some
will
risk.
only move maybe when you apply some 1000 kg of force. But that is again more complex discussion. In theory, what we say, because it is a roller support, this fx will not be developed and it will generally release. So you will not, you will just give release in your model, and
So,
moment will also release.
so FZ we should not release in 3D.
Fz you should not release. No,
In
for
2D
this model
it's
only.
not there actually. In 2D it is not
In
there.
2D this is not there. So anyways, this is already considered as 0 in 2D because it doesn't exist in 2D model. If you are having this kind of model, to z is not there in picture.
Mhm.
So 2D is only for our studying purpose. In reality, there is nothing like 2D.
So
Everything is 3D, right?
keep always FZ and FX release only. That is better.
For 2D. For 3D, you can keep FZ. You will get some reaction, and for that reaction, you can design your connection.
Okay, okay.
But in reality, why you will not get the any values in FZ? Even if you keep this as restrained, if you are having this kind of model, you are applying all your bridge loads over here, and you are doing the analysis. What forces you will get? You will only get Fy, and here you will get Fy. Whatever forces are there vertically, maybe half of will be split over here, and you will get some. This also will become zero. So practically, you are not applying any force in wind direction, right? If you are applying some forces in direction of wind, only then this Fz will be developed. Here also, if you are applying some wind forces, because of the wind forces, because this is release, this will just rotate like this. This will just move like this, like it is shown in the picture right now. So Fx is release, moment is release, all other directions are fixed. But because there is no loading in those directions in general, that value will be zero unless you apply wind in that direction. If you are applying some forces in z direction, then you will get Fz reaction. You will get some value over here.
Okay, okay. Thank you.
Okay. Okay. Yeah, Ramarjun bridges for bearings. Yeah, for bearings, those kind of releases are generally given. Let's come to our discussion. Pin support is done. Second is when we are applying force in this part in the node. So now let's see how you can apply force in your node. Loading, new load case, add nodal load, and I want to apply load in x direction. X direction value is 10 kilonewton. Add close. So this, use cursor to assign. I want to apply it over here. Click over here. So this is the force what I have applied. Similar to my example. What is the example? This example. If you want to see this value, right click, labels, load value, apply. Okay. So 10 kilonewton is applied. Both are pin support. Let's make this roller as per this support. This is roller, so I will convert this into roller. Yes. Now let's run the model and check the results. Load case to MZ. You can see similar to this figure. Because you are applying force over here, force will be transferred. Let me again slightly explain. Roller, pin. Because of this force will be transferred directly over here, and because of this force being transferred over there, this is the bending moment diagram, and same, because here you are having bending moment, that will be transferred over here, bending moment. Because this is roller, nothing will be transferred over here. Okay, but similar case, if you are having a roller over there, let's see if I have that example. No, that is not covered. But let's see how it will happen if I'm having a pin connection over here as well. So all these are interview questions. In interviews, most of the time, they ask you related to the BMD diagram for various kind of frames. Still, you will be getting, I think, the same. Yes, now here also same bending moment is developed for the frame, and here it is going upwards. This is the difference because of the both pin supports. Okay. Now next one, let us see what will happen in case of UDL. Now I will be applying UDL. Add member load. This one -10. Add close. UDL of -10. Use cursor to assign on the top member. The value is -10. Let's check this one. I told you, whenever you are having UDL, your bending moment will become curve. Initially it was straight line for point load. For UDL it will become curve. Okay, the values you can check it by yourself. So this we have checked. When you apply moment, how you have to apply moment, let us see that now. If you want to directly apply moment. Okay, let me show you this one. Yes, the figure is matching. The values you have to validate on your own. Okay, so the figure is matching. Next one we want to do, how you want to apply moment at a particular point. So loading, add port kind of load. In this I want to add only the moment, member, concentrate moment, or you can go for where that force was applied. Let me see. The third example. At this node, moment is applied. So nodal load mz, what is the value? 10. 10. mz 10. Add, close. This mz, use cursor to assign at this node. At this node, okay, it's applied. It's not able, I'm not able to see, but it's applied. Yes, now I'm able to see, but the direction, I want to change the direction. So I will just change the sign. Yes. Run the model, run the analysis. Let's check the bending moment diagram. This is the bending moment diagram for both pin support. If any one of them was roller, the bending moment diagram would be something different. Okay, so this is for pin connection, both pin connections. Let us see for roller. Support, roller. Let's assign over here. Now here you can see if you have roller support, only moment will be there in your beam. Okay, so this also we have checked, the validated the result for rollers. This you can try it on your own. Okay, this we have tried. Okay, let me show you this thing. How if you want to apply, if you want to apply force in other direction. Let me just show you that once. Load case 5. Member load. You just need to change the direction. Now it will be global X and the value will be 10. Add, close, global X, use cursor to assign and click on this. Okay, in this way you can assign the value in X direction as well. The bending moment diagram, here it will be curve, this will be straight. Curve, straight. Okay, values you have to validate. Then we have seen both side pin connection, point load we saw, UDL you can check it on your own, or I think we already saw this. For both side fixed support, now how you want to assign fixed support? Analytical modeling, support, create, fixed. In fixed, all the things will be restrained. Add, all the supports will be restrained, and I am assigning it to both the supports. Now you can run the analysis. That was which case? Yeah, case number 1. MZ. Now you can see, because it is a fixed support, you also have bending moment at the support. I hope you understood the difference between all three things. When this becomes pin, the bending moment is starting from here. And when any one of them becomes roller, then there will not be any bending moment in the column, only the beam. These all things you should understand. Similarly, whenever you are having fixed support, there will be certain moment which is developed in your support. These all things we have seen. Okay, when you are having cantilever, only one's fixed and other is free. You can try this. Let's try one example, then other things you can try. Uh, let's try maybe this one. Let's try this. When I'm having some moment at point D, go over here. Support, no support is your cantilever. So assign this part. Here it is free, only one fixed support. And in loading, let's create a new load case 6, add nodal load, mz is again 10, add close. So this value I can assign at this point. Again, maybe I need to change the direction. So -10. Okay, now let's run it. Run the model. Yes, correct. Matching with the results. Everyone tell me in the comment section, are all these things clear to all of you? I will be sharing with you this PDF. You can try all these models on your own. Okay, one thing I want to tell you, ask you, what will happen if I'm having this kind of member and both these supports are a roller? What will happen in this case? What will happen in this case? Model will become unstable. So this will become unstable and you will not be able to analyze it. Similarly, if you are having this as pin support and this as free cantilever, what will happen in this case? Again, this will become unstable. That is why we require, if you want to have one side cantilever, at least the other side should be completely rigid, fixed. So this is stable. I don't want any one of you to try this model and tell me that my STAAD.PRO is not working fine. I'm getting error. Don't try this thing and tell me my STAAD.PRO is I'm getting error. Okay, this is common sense. As a structural engineer, you should know why it is stable and why it is unstable. Logically, you just assume you are applying some force over here. Maybe here you are applying some force in this direction. What will happen? Your just member will, your model will just move for the force applied. So if it is moving, this is not static structure. It becomes dynamic. It becomes moving structure, and moving structure we are not analyzing right now. So this will work, not work. And similarly, in this case, if you are applying any force in downward direction, what will happen? This will just rotate. It will directly rotate and fall down. This is also not practical. But in this case, if you apply this force, it will not move. It will, maybe it will deflect slightly, but it will not fail. Even if you apply force in downward direction, maybe it will deflect, but it will not fail. So these are stable. This is stable. These two are unstable. So let me also show you one unstable model so you understand what kind of error you will be getting. Okay, support Let's assign pin support. And now if I run the model, what I will be getting? Let's see. Run. Zero errors, one warning. Right now, because I'm modeling this as 2D, I'm getting one warning. Let's see the warning. Or first, let's see what kind of moment I'm getting. Here it is zero. And see, practically deflection is infinite. If you because you see the model has already fallen down. If I want to measure the value of deflection, let's see. You are getting some big value 9.97 into 10 to the power 11 mm. Yes, so this is practically not possible. Something is wrong. If you go in utilities analysis output, instability at joint 3 direction X warning, you are getting instability at joint 3. Okay, so this is not correct. Now let's go back. This we have done. Now for two support, I want you to try this on your own. Okay, for two supports, two member, these all things you will try. Now let's discuss trusses. Is frames clear to all of you? Ramarjun, in this case, what will do? Means in which case? In case of instability. If your model is unstable, that means you are doing something wrong, and that is not practically possible. So if you are asking what I should do in this case is not allowed. This is not allowed. Either you have to change your support. Yeah, the only option what you have is change your support. If you cannot give pin support in this model. Practically also you cannot give pin support for this structure. It will just fall down. So unstable means it is not possible. Normally some space frame also come like this. No, no space frame will come like this. Frames. Can you explain me what you mean by space frame come like this? See, I hope I am understanding your question. If you are having this kind of space frame, okay, a whole 3D structure, and in this 3D structure, if you are having pin supports, this is possible. This is not unstable. This is stable. This is stable. But in this example, if you remove these two supports, this becomes unstable. Right? If you want to work on this kind of structure, you can convert this into fixed support. Again, this will become stable. If you are having this kind of car shade, here you want to park your car, you only want to give this opening, then you cannot give pin support, you have to give fixed support. But if you are having maybe some bigger area, something, you are having some, I hope you understood, when you are having some other area, then pin connections is possible. I am not telling that pin connection is not possible at all. This is possible. This is correct. This can be worked. This is stable. Okay. Coming to our discussion. Now let's start with trusses. Trusses also some things you have to do on your own. I will do some. This is simple thing. Let's not waste time in doing this. Problem one. Yes, whenever Tushar is telling the right thing, the advantage of pin support, whenever you have your pin support, it is easier to design it because you will not have any moment. But in certain examples, whenever you want to work on any cantilever pole, then pin support is not possible. Then you have to go for fixed. Okay. We only have 10 minutes. I will explain you one problem and then we can continue tomorrow. This is very simple. If you are having a simple column, cantilever fixed at bottom, if you apply force, that same force you will get as a reaction. Problem number two, this also I want all of you to try it on your own. Okay, this you have to model. One side is pin, other side is roller, and you have to apply 10 Newton, 10 Newton, and 10 Newton, these forces, and you should get reactions as 10 Newton and 20 Newton. And in this member, okay, let's do one thing. I wanted to, today we will do problem 2 and problem 3, then 4, 5, 6. We will do tomorrow and start with 3D. Today is the last day when we are discussing regarding two-dimensional modeling. From tomorrow, after we will slowly move towards three-dimensional. Okay? So I will show you this one. Let's do it. New plus 1. Create. Okay, start with 0. View, let's view this from front view. Second point is at a 5 meter distance. B is 5 meter. So Y will become 5. C is again at 5 meter. So X 5, Y 5, and Y 0. Okay, these are my 4 points. Geometry, add beam, 1, 2, 3, 4, and diagonal element 5. These are my members. Properties, what property I can assign? This I will just close. Property maybe, yeah, I can assign any of the properties. Section database, Indian ISMB 100. Close. Assign to view. Assign, yes. Now material steel specification, I don't, let's see related to specification later on. Support, create. First is pinned support, and what's the second support? Roller. Create fixed but mx, my, mz, and fx. This will be my roller. Add, assign to this part, and this one to this part. Okay, and loading, what I have to apply? 10 kilonewton and 10 kilonewton. Okay, so loading, add, not this one. Go in load case detail, then click on add. Load case 1, add, close. Load case 1, add nodal load Fy minus 10 kilonewton, add, and second nodal load is minus 10, and I think x direction is 10, add. Okay, so this nodal load will be over here, and the second one will be over here. Let me confirm. Correct. Okay, 10, 10, 10. Now let's give the analysis command. We have not given the analysis command. Okay. Also, whenever you are working in truss, uh, first let me analyze it. Run analysis. Then I am getting one warning because I have given the command of, I have not given the command of plane. Let's give that command. Stad plane. Run analysis. Zero warnings. View. Front view. Now when you go in post processing, what I wanted to show you, first let's see the reactions. 10. Okay, go in, select text, move this. You can see 10 and 20. So these values are matching, 10 and 20. Now I only want to show you, okay, reactions are matching 10 and 20, 10 and 20. Now let's see this. AB is 10. What is AB? Vertical member is 10. Okay, so for this, what I can do? Tension, compression, these are all are axial forces. So go in results, Fx, beam results, Fx. Okay, and if you want to see the values, first one you can see 9.984. Anoid, let's see if we see the values. Beam, axial forces, anoid. No, the values are all mixed. It's not, I'm not able to see. Let's remove it. Here you can see in this table, Fx for this member, the value is 9.984, and what I wanted the value of 10. Secondly, for this member, 14.096, and what I was expecting, 14.14. And third, this member, again 19.98, 20. So if you want to get the exact values, we need to tell STAAD.PRO that this is a truss and I want only axial forces. Because right now what is happening, you are slightly getting some bending moments, but in truss, in reality, you don't have any bending moments. So let's try one thing. In specification, now for the first time I'm showing you specification, beams. Go in specification, go in beams. First option, here you have option truss. Click on truss, add member truss. So let us assign member truss to the whole view. So now all the members will be treated as truss. Four warnings. Let us see those warnings later on. First, I want to check the results. Beam results. Yes. Now you can see this member is having axial force of 10. This member is having axial force of 14. This member is having axial force of 20. So whenever you are working with truss, you need to either specify truss, or you can Maybe if I delete this, I can directly go into command files, and here I can write STAAD.PRO. Run analysis. Now you are getting 0 warnings. Let us see the results. Again, you are getting 10, 14.14, and 20. So you have two options. Either you can specify STAAD truss, but the problem is if you are having a big model where you have combination of truss and beams, then you cannot just mention STAAD truss. So the better option practically is for your truss member, you can go in specification and specify separately as truss, and then you can just model them as STAAD space or plane, whatever. You will get some warnings, but you can ignore those warnings. Okay, so right now let's keep as truss. Kindly everyone answer and tell me, is this clear to all of you? Kindly answer. One small thing, one small, yeah. Tomorrow I will be explaining you this thing. Difference between why we are getting difference. What is the difference? When I am just modeling this as a normal structure, normal frame, normal beam, I am getting different results. But when I am modeling as truss, I am getting different results. In short, I want to tell you, if you model anything as normal thing, if you are modeling this thing directly, this is pin, this is roller. STAAD will assume that this is rigid connection, this connection, this connection. These are rigid connections. But when you model them as truss, STAAD will assume that these are pin connections. In reality, also it is a pin connection, right? In reality, how you are modeling trusses, this is one member. Here you are having pin, this is another member. Here you are having pin, this is next member. Here you are having next member. Again, that is connected by pin, and you are having one diagonal member. And here you are having some kind of support like this, pin support. In reality, this will be the type of connection what you will be having, and you are having some force applied over here like this, like this. So this is realistic. Okay, and it is not rigid like what STAAD was assuming earlier. Because it is assuming this as rigid, some bending moment is generated. Some bending moment is generated. But for pin connection, zero bending moment is generated. Bending moment is not generated. So truss only carry axial force. Normal members have your axial force, shear force, bending moment, everything. But in trusses, they only have axial force. This is difference. Tushar, yesterday I was asking for overhang beam for both sides resting on main beam condition. Tushar, you are asking regarding normal overhang beam, this kind of beam. This we discussed yesterday. Resting on main beam. What do you mean? Okay, maybe you are telling Three dimensionally, if I'm having this kind of member and my primary beams are something like this, which is overhanging. This is what you are trying to tell. Yes, these kind of structures are there where you have your primary, where you are having this black color, maybe primary beams, and red colored secondary beams. This can be secondary beams. These can be your primary beams. But what is the question? This you can consider as pin support. Whenever you are modeling this secondary beam separately, you can consider this as pin supports and model it. For secondary beams, the support condition you can apply as this pin support. If you want to apply, if you want to model this separately, then you have to assign wherever it is touching this part, and this part you can assign as pin support. But if you want to model this whole thing in STAAD.PRO, then you can directly model it like this. You can model this 3D element in STAAD.PRO like this, and maybe your primary beam is supported here. Primary beam might be supported somewhere. So give this kind of support arrangement and apply and run the model. It will work fine. No condition has to be applied for secondary beam. Secondary beam is directly resting on your primary beam. So just model. This is one element. This is one element. This is one element. This is next element. These are next elements, and give these as pin supports. And you can apply whatever loading you have. Maybe you are having some loading on your secondary beam. You can just model this thing and run it. No need to give any specific separate command. That STAAD.PRO will transfer the load automatically from your secondary beam to primary beam and do the analysis. But if you only want to model the secondary beam separately, like if you want to model this thing separately without primary beam, this also is possible. Then in that case, you have to give this as supports over here. This is one support, another support, wherever it is touching. Pin supports. Then you can also model this as separately.